Hi everyone, I hope you are doing well. Welcome, we have done so many of these. Searching and sorting is the job today, so I hope you are all doing okay. Please say hello in the comments. I will introduce you as warmly as I can muster, although you get a day off tomorrow, don't you? Which is one more day off than I get, but anyway, that's... Don't wish to sound bitter about this. So let's have a little look at quiz time, see if we can remember a few things. Please say hello. Who have we got here? Let's have a look. We have got, let me put this first one up actually, and then we'll go from there. This is a bit of a recap from last week. Hi Aditya, how are you doing? Great to see you. And hi Sergen, how are you doing? I see our two teams are meeting on Wednesday. That'll be quite interesting. So can we remember, who else we got here? We got Hash Brown. Hi Hash Brown, how are you doing? Is it your birthday today, Sergen? Oh, I didn't realise we should all sing you happy birthday and give you the virtual bumps. I'm sure they've been outlawed by the Geneva Convention now. And Flynn, how are you doing? Great to see you. Oh, two. Two is the answer. I was sneaky and I changed this from last time, hoping that I could catch you out with the print. Happy birthday to you, dear chap. Did you get anything exciting? Did you get a new Liverpool shirt? And it is a syntax error, so I can ding that one, and I can ding that one, and I can ding that one too. So that's pretty outstanding. Easy peasy, isn't it? Syntax versus logic error. Although in that, yeah, Aditya says that correct, syntax error, that's exactly what it is. Don't forget how to explain a syntax and a logic error, okay? So that is, that's really, really important. Okay, so... There we go. Okay, so let's go on to the next one then. This is a nice, easy one based around flowcharts. Shopping tomorrow. Exciting. Anything exciting on the menu? Have you got anything in mind? Shopping for clothes. Is it going to be clothes you're going to go for? Let's have a look. Ooh, Aditya's come straight back in with a... In a flowchart, what shape would you use around does the password contain a number? Do you know what, Aditya? You are absolutely spot on. Let's go for the ding there. It is the diamond. That's obviously the one for your decision box, okay? And don't forget, if you're in section A of paper 2, you can use that. Football boots. Ooh, okay. What are you going for? Is it a pair of Adidas or Nikes? Or do you say Nike? I know they're flipping expensive though. Okay, let's go on to... Have I got another one here? Hash Brown, I cannot comment on that, but I agree. Although, do you know what? I've got a feeling they will overturn City. Yeah, very nice. I wish that stuff fitted me, but I find the Adidas stuff just fits my feet better. Yeah, let's not abuse Sergen on his birthday. It's just not fair, is it? Although, you know, Liverpool fans probably deserves it. So yeah, Diamond, you are spot on. Absolutely brilliant. So... We've got quite a lot to do today. We're going to cover 5 of these. So I'll put this PDF out there for you so you can look at these. And I guess moving through the stages, we're going to look at the 5 today, the 2 searches, the 3 sorts. And I guess that first of all, it's building an understanding of how they actually work. And then I guess the next part is being able to show that on the page so that you so that when they give you a list of words, you can show what you actually need to do with it. So 2.1.3, we're into the second half of the paper, and we're looking at searching algorithms. All right, so we know that lots of software requires you to search or to sort data, okay? In terms of searching, the 2 we're going to look at are linear and binary. And I think that conceptually, these are pretty easy to understand. So did I say the final stage is probably getting your heads around the pseudocode? And I would say, given that paper 2 is probably the most tricky bit in terms of creating that pseudocode, maybe the pseudocode I'm going to show you here could be worth spending a minute or 2 just going through it so you actually understand what each line does. All right, so linear search. The logic behind this algorithm is that you start from the left hand side, and one by one you compare X, which is your search item, with each item of the array. And we know an array is a fancier computer word for saying a list. And if the item that you're searching for matches with an element in the array, you return the index, which is the place where the number is. So you see the numbers we've got on the top. The index is beneath in this little diagram. We've got in this table you've got here. So you've got, if you like, place 0, 1, 2, 3, 4, 5, 6, 7, 8, and then you've got these random numbers, okay? And you start on the left-hand side at 10, and you basically work your way through. So without wishing to state the obvious, so we're looking for number 5, okay, which we can see is at position 3. And don't forget, when you ask about why we're adding 1 back in afterwards, it's because we're starting at index 0, right? People always get confused by that. So we start at index 0 and we say, is 10 5? No, it's 10. We go to 1, and so on. So you just go through them one by one until you find the item that you're looking for. If they do a question on this in the exam, they're probably going to base it on you just in words having to express that. So understanding it is one thing, but being able to actually express it in words is just one level more abstract. So make sure that you've got the vocabulary to talk about the search item, you know, matching with the returning the index and so on, and the element you're looking for. Okay, so just think about how you're going to voice that in the exam. It's actually quite straightforward. So here's the pseudocode, which I think is worth. I'm probably not going to have time to go through all the pseudocode today. Okay, because linear is a line. So in other words, you're going in a line from A to B, if you like. So it's literally, you can draw a straight line. You're not, and you'll see later when we've done some more of these searches and sorts that they don't all work this way. So this just starts at the left, and you can draw a straight line to the right hand side, and you keep going until you hit the item. That's the idea behind it. Does that make sense? So that's why it's a linear search. So this linear search pseudocode, up at the top we've got our array. So the array is being declared as being called people. That's the variable where the array is stored. It's a one-dimensional array, so it's just one list. A 2D array. A 2D array is like an Excel spreadsheet where you've got columns and rows, if you like. So that would be a 2D array, and you don't have to worry about 3D arrays for this. So now the idea of a flag being used, that found is set to being false, and then you're going to check until it's true, and at which point it's true, then the search ends. Okay, so X is 0. Search for equals input, enter a name to search for, so you put in the thing that you're looking for, and then while found is false, so while it isn't found, and X is less than 5, that's because there are 5 search items there, then basically you search through each item. Okay, and you've got the if then else in there. Okay, so you've got a bit of selection, and then you've got the X equals X plus 1, which moves it up to the next index number. And if you just spend the next sort of, what have we got here? How you doing? Thank you for being here, dear boy. I hope all is well. Welcome back. So this is pretty much it. Now, I would say to you that I can talk to you about this algorithm for ages, but if you actually take this algorithm and compare it to maybe have some cards or some, you know, anything that you can sort and go through it and actually follow this algorithm all the way through, it'll kind of help hugely when it comes to that section B of paper 2, which you guys here in particular, looking for that grade 7, 8, 9, that's going to be a difference there, because you're going to be able to hit those sort of 6 out of 6 and the 8 out of 8. Indeed, it is the birthday boy today. He's getting some football boots tomorrow, we've discovered, some Nikes. So yeah, it's all good for Sergen. Okay, so that is the linear search. Right, where are we? 38. Okay, binary search next. Binary search is more efficient. That's the other thing, and I haven't got all the details here, but you'll need to know why you would use one search rather than another. And this is generally, with this one, it's quite straightforward, because the binary search is more efficient, but for a binary search to work, the list has to be ordered. This is very depressing. Yes, buy him a Man United shirt. That would be an excellent one. Or an Everton shirt. That would be even more insulting, I would have thought. He can use it to wash his car. So binary search, more efficient, but the list has to be sorted in advance of the search. So that's a problem. And that's something that they can pull out, asking you a sort of 1 mark question, 2 mark question. Yeah, I think we've decided that now. So that's the thing. The list has to be sorted for the binary search to take place. So the logic behind the binary search is this. You find the middle element of the array, which, by the way, you do by going to the halfway point, which means you add index 0 to whatever end index you've got, you know, the number of different elements that you're searching. So say if you're searching 10 items, you've got 0 plus 10, which is 10. You divide it by 2, which is 5. And if you need to round, you round up rather than rounding down. I think that's all you've got to remember, really. Well, yes, you would need another. That's a really good question, actually, Ditty. You would need a separate algorithm to sort the list, but you would just simply use a different algorithm to sort. You wouldn't use this one on a list which isn't sorted, if that makes sense. Okay, you just wouldn't do it. You wouldn't do this search in an unsorted list. You would use a different one. I mean, there are many more searches and sorts than we're doing here tonight, this evening. And you need to get to GCSE and get to degree level to learn how to do those. But the fundamental principles kind of hold true. And most searches and sorts you would look at after this point are, I suppose, offshoots and offspins of this, if that makes sense. Okay, so logic behind this is find the middle element. If the middle element's the thing you found, you can return the item as being found. If not, you ask yourself the question, the thing I'm looking for, is it bigger or smaller than the middle element? And depending upon the answer, you're then going to discard either the left or the right-hand side of the list. So it's kind of, you're cutting the list in two each time until you find it. Okay, so let's have a look at that in a bit more detail. So say, for example, the top table you've got there, we have got 9 elements there. And so therefore we've got 1 to 9. The middle element is, and we're looking for the number 3, okay? Indeed, we haven't yet sung him happy birthday. I think we could possibly do a virtual rendition of that, or even wait till he's in class to make it worse. Well, not in class tomorrow, are we? So find the middle item and then ask the question, is it higher or lower than our search item? So we are looking for number 3. And if we go to the middle part is 4. That's the item there. And we ask ourselves the question, is it higher or is it lower? Well, it's higher. Sorry, it's lower. So therefore we discard the right-hand side of the list. And you just keep going. And you can see why this lends itself to being programmed, because you're just doing the same thing over and over and over again until you find it. Now, if you wanted to really make your head hurt, you should try writing some pseudocode before this, or have a go at it, and then compare it to the pseudocode that I'm going to show you and just see how accurate you were and see how efficient your search was. So when we do discard the right-hand side of the list, we go to the middle point again, and we find the number 3. So boom, it's done. And you keep going and eventually you'll get there. Okay, so here is the pseudocode for the binary search. Notice at the top there how a function is declared, something that would have got you an extra mark in that assessment we just did. Start is at point 0, is at index 0. End is the search list length -1, and don't forget it's -1 because we start at 0 rather than starting at 1. Okay, so that's the -1 there. And while left is less than or equal to right and not found, another way of voicing it, midpoint equals start plus end. So index 0 plus index 10 divided by 2, which is 5. So that's our midpoint. If the search item's at the midpoint, I'm on line 7 by the way, if the search item, 1, 2, 3, 4, 5, 7, 7, interesting. If the search point is the same as the midpoint, the search item's been found, else split it in 2 and do the same thing and keep returning midpoint until you find it, okay? So another way of voicing it, but if you spend a bit of time with this and just work your way through that line by line, we haven't got time to do it today, it's going to be a 10 or 15 minute job and it will make your head hurt. But at the end of it, you'll have this sort of moment where you go, okay, I see. Now you might not be able to reproduce this exactly as is because you're not going to have to produce anything that complex, quite that complex in the exam. But if you can get your head around this sort of pseudocode, this kind of an algorithm, it'd be really, really helpful for paper 2. Okay, so that is the binary search. So that's binary search is sorted. Where are we? 15 minutes left. This is okay. 5 minutes per sort. Right, bubble, insertion and merge. Each got their advantages, each got their disadvantages, and each work in a slightly different way. And listen, if today all you're getting is a flavour for how this works, that's fine. Go back and look at the PDF in more detail afterwards. Right, so bubble sort. It's a simple algorithm and it's used to sort a list, okay? It works through the list by making comparisons between adjacent pairs. So in this example, you've got Yes. Thank you, isn't it? Do you know, I like the colour of my hoodie. I've had this hoodie for about 15 years. I just like it is very red. I like the colour. It's a slight orange, actually. You know how you've got your thing that's just very comfortable? I just like wearing it. Okay, so we've got 3 and 2 here. So do 3 and 2 need swapping? You assume that the first one is already sorted, right? Do you need to swap the first 2? If so, you do. Then you move along to the next pair. So 3, 2 gets swapped. So then 3, 2 becomes 2, 3. Then you check the next 2, 3, 4. Do you swap them? Do they need to be swapped? Yes or no? So is 3 less than 4? They're not swapped. And you just work your way through in pairs like that. You sort of snake your way down the list one at a time. I mean, I suppose you could argue, Ditya, this 2 is, yeah, let's not get into that. And it works this way, that way. I mean, I think, by the way, the reason it's called a bubble sort is this idea that things bubble their way towards the surface. However, once you've done all of that, and you may be ahead of me here, you may need to have multiple passes of the data because you're only swapping 1 each time, okay? So the list, even though it's been the bubble sorts run once, it might still not be sorted. As you can see, let's work our way down here. So this is a continuation of it, the second loop. So the first loop, it wasn't sorted. So question for you in the comments, please. How does the computer know how many passes to do or when to stop doing passes? The passes is when it goes through the second loop of doing all of the swaps. How does the computer know when it's actually been sorted? Any ideas? You lot, by the way, are super clever, so you can figure this out. How would the computer know? What wouldn't have happened, does that make sense? Yeah, if it doesn't need to do another pass. When all items have been compared, yes, this is true, Aditya, but my question is, how does the computer know? I know it's okay. Now look at this, when you can't swap no more. So what would have happened in the last pass for it to not need to do another one? We're getting there. We're one more step away from it. 2 very intelligent answers there. What would have not happened for an entire pass for the computer to know? And I know I'm saying the computer knows. Computers don't know anything, right? They're programmed. Yes. When you can't... Yes, excellent. Bogdan, I haven't forgotten. I made a promise to Bogdan and all of you last week to send you the algorithms. I will do this, okay? And my apologies for not doing it. Bogdan is absolutely spot on. If a whole pass is made and no changes and no swaps are done, therefore it's sorted. It's sorted. Does that make sense? That's how it works. So exactly, Emma, when it does a whole pass and nothing happens, then it's sorted, right? I just think conceptually that's really, really, really important. I did say, I'd never said you weren't intelligent. I might have said you were a pain. I never said you weren't intelligent, to be fair. I'm consistent in my abuse. All right, so that's good. I'm really happy with that. I think that makes sense. That was good reasoning, chaps. That's the bubble sort, okay? Which means we are done here. This is what the pseudocode looks like, 12 minutes left, so I can't spend much time on this. But again, and that was a decent test, by the way. Spend a bit of time with this. I haven't got time to do it now. Spend a bit of time going through how it works. If you're being really daring, try and write it in pseudocode. It's challenging, admittedly, but if you go through it line by line and you go, okay, I see what that does, I see what that does, because by now it should all be becoming more sensible. You know what the double equals is, you know why it's doing +1, you know what these symbols mean, you know what the flags are, sorted equals false, sorted equals true, all that sort of thing, which just makes that section B of paper 2 that little bit closer to giving you the marks you need. All right, so that is our bubble. Right, insertion. I need to speed up, I've only got 10 minutes left. It's similar. However, in this one, the first element of the array is always considered sorted, not in the bubble. The bubble sorts the first 2. I was incorrect to say that. And then we go on to the second element, which we compare to the first. So let me go straight into here and try to show you how the insertion sort works. I've got a diagram here. Is that there? That's the merge sort. Bear with me a second. Let's go back to here then and go through this bit. Okay, the first element's always considered sorted. I'm down here at bullet point 2, okay? Then we go on to the second element, which we compare to the first. So you compare the second to the first. If the second element is smaller, then the two elements get swapped, okay? That's how the insertion sort works. So on this one here, well, I recommend you just simply work your way through there. I'm just aware that I've got 10 minutes left and we're not going to have time for any quizzing at all. That is the insertion sort for you. And of course it's called the insertion sort because it's inserted into the right place, okay? So if we look at 8512, the 12 is inserted into the correct place. Then it goes along to the 59. I'm now the third line down and it inserts that into the right place. And it just works its way through like that, okay? The pseudocode for this is actually quite simple compared to what we've seen before. Again, another different flavour of pseudocode, because pseudocode, as we know, it can take many forms. Look at the way the function has been declared at the start. That could be worth a mark in the exam for you. For sort code equals 1 to sort list length -1, that -1 again, okay, and so on. So I'm not going to have time to go through that now, but have a look through that one to make sure that you're happy with it, okay? The merge sort, I'm speeding up, so I've only got 9 minutes left. Right, the merge sort. If you look at the top of that diagram, right, the unsorted list 2, 45, 6, 9, 15, 12, 7, 8, it first of all splits them into individual items, which it does by line. So line 1, line 2, line 3, line 4. Can you see by line 4, they're all separated out, so they're individual items. So it splits them apart and then merges them back together. And then it merges them first as pairs, then as 4s, then as 8s, then as 16s. It depends how big your list is, okay? So if you look at 1, 2, 3, if you look at the fourth line, yeah, I think merge sort is the easiest because it's the one that makes the most sense to us, and it's probably how we would actually sort things. It is how we'd sort things, isn't it? You'd put everything apart and then you put it back where you wanted it. So I think that's why, because conceptually look at it and go, yeah, that makes sense. I mean, the insertion sort makes sense, is that you pick something up and you put it back in the right place, but it's kind of a bit more fiddly, isn't it? But I do think, even if today all you're doing is getting a flavour for how these different searches and sorts work, then that's a good first step. In the exam, they'll give you a list and ask you to demonstrate how it's done. So think about how you might do that. So can you see on 1, 2, 3, fourth line, everything is separated, okay? And then line 5, so 2, 45 go back exactly as they are, 6 and 9 go back as they are, 15 and 12 get swapped because 12 comes before 15, and 7 and 8 stay as they are, which gives you then 2 sets of 4. And then you're basically doing the opposite of splitting it apart, except you're putting it back in order. I think conceptually that's quite easy to understand. It's called a divide and conquer algorithm because they're divided and then it's conquered, I suppose. So that is that one. That is your merge sort. Good, quiz time. I wanted to leave enough time, so we've got some good questions here. Look at the diagram below. This shows a nearly completed merge sort. What 4 values will appear in the yellow boxes? I know you like the quizzes. I rushed the insertion sort slightly, guys. My apologies for that. What do we think? What 4 values will appear in the yellow boxes? What do we think? Oh, I've got a countdown timer somewhere. Where is it? There it is. I never look at it, and you never. There we go. 20 seconds. What do we think? Oh, Hash Brown has come in with a very quick answer. 2, 4, 5, 6. Aditya has as well. And Bogdan has come down with 2, 4, 5, 6. Emad saying 2, 4, 5, 6. That was a very good race there. Shall we see if the answer is 2, 4, 5, 6? 2, 4, 5, 6. 2, 4, 5, 6. That is outstanding. That was very quick. Well done, guys. That was very impressive. Okay, let's go on to the next one. What have we got? 6 minutes. Okay, look at the diagram below. How many iterations would it take? This is a bit nastier, maybe. Would it take a binary search algorithm to find the value 19? No pressure. Who was it first that time? Hash Brown Gaming. You were on fire. That was quick. You were straight in there. Hash Brown followed by Aditya. What? Swift Blades come in with 3. Let me give you a few seconds on that one. You have 20. Emad's come in with 3 as well. 3 iterations. One more answer, and I can see that Bogdan's come in with 3, Emad's come in with 3. Okay, you guys look like you know what's going on here. The answer is 3. Woo! Really good, Swiftblade. That was stunning. Well done. Absolutely brilliant. 3, yeah, iterations. Yeah, good. 3, 3, 3, 3, 3, 3, 3. All right, brilliant. What do we got? 6 minutes. Okay. Look at the diagram below. What type of search algorithm could be carried out on this data in its current form? What type of search algorithm? And maybe you could put down why that be the case. What do we think? Oh, Aditya's got in quickly here. I can see he's the first. Aditya's come in with linear. 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 I've got a feeling. Ooh, Aditya said binary. Because the array is sorted. Because it's unsorted. Bit of a dispute here. Shall we see what the answer is? It's a linear search. So that was Bogdan and Aditya and okay. So outstanding. Okay, question 4. Long one, this, guys. 4 minutes. I will finish on time. Yeah. A company has thousands of customer entries in its computer system, and this is very OCR, the way they give you a long spiel like this. Each customer has a 10-digit ID number, which the company uses to sort the list of customers. When a new customer signs up, their details are added to the end of the sorted list. Which algorithm would be best to use to make sure the list remains sorted? There is an assumption that you've actually stayed awake to read all of that, but what do we think is the answer? Man like Paul says bubble. I think, was that an old answer, Bogdan? I can't remember. Was that an old answer, insertion sort? I can't remember. I think that was an old one, Bogdan, was it? I can't remember. So we've got Swift who says bubble. We've got Man like Paul who says bubble. Swift says bubble. Aditya says bubble. Man like Paul says insertion. I'm going it both ways here. Emad says bubble. Shall we see? The answer is it's an insertion sort. So that is outstanding for, I think that was Bogdan got it right. So this idea of knowing which one you would use, yep, you were spot on, absolutely spot on. Well done, really, really good. Okay, I can tell. All right, so what's next? Question 5. If a computer has a low amount of memory, but you need to sort a large number of items, you would probably avoid which algorithm? Now, this is a bit of a challenge, given that I haven't actually given you the answers to this yet, but let's see if you know it. So this is where you need to go and look at your revision guides and make sure you're happy with which algorithms need more memory, which algorithms run faster. Oh, Bogdan straight in there with a merge sort. Anyone like to add to that? Are we happy with Bogdan's answer? Man like Paul coming with the merge. Hash Brown saying merge. Emad's a merge. Well, if all of you genii coming out with merge, I don't think we can really argue with that too much, can we? And the answer is it's a merge sort. Whoa, that's really good. Okay, that is outstanding. Swiftblade had a merge as well. So that is really good. We are so near. I think I've got one more question for you. Last one. 2 minutes to go. Question 6. The diagram shows the passes of an incomplete sort. What type of algorithm is being used? I've got to thank Miss Silver for these questions because her questions are awesome. What type of algorithm is being used, do we think? This is the last one. Here's the last question. 1 minute to go. What do we think? What type of algorithm is being used? What do we think? Any ideas? Ooh, I can see the answers are coming through. Bogdan is in with the bubble sort straight away. So's Aditya, just after Bogdan. It's 59. Swiftblade with a merge. Let's see what it is. Okay, so the answer is bubble sort. All right, so that was a ding again. Where's my ding? It's there. That was outstanding. All right, so we have reached 1859. It's about to turn to 7 o'clock, which means that we will all turn to pumpkins and vanish. So sequence, selection, iteration next time, programming fundamentals. So make sure you are there for that. Guys, it's been a massive pleasure. I will not forget, Bogdan, to put that stuff onto Satchel 1. I must tell you it's at school, so I'll do it tomorrow. But I will... yes, The Terminator was a great movie, for sure. It stood the test of time, and just like Arnie, I'll be back next week at 6:30, and I'll see you then. Guys, it's been a pleasure. Have a great week, and have a nice day off tomorrow, he said, really bitterly. See you next week, guys. We'll see you later on in the week. Take care. Bye-bye. Bye-bye.